Good morning to one and all. I am Ramesh, Assistant Professor in the Department of Aerospace Engineering, SNS College of Technology. Today, I am going to discuss about the single-stage rocket system and the importance as well as the need for staging. First of all, what is a single-stage rocket system? A single-stage rocket system is a launch vehicle that reaches its mission objective using only one rocket stage. Unlike multi-stage rockets, where empty fuel tanks and engines are discarded during flight, a single-stage rocket carries all of its components from launch to mission completion. Single-stage rockets are among the earliest and the simplest forms of rocket systems. They are widely used in sounding rockets, tactical rockets, experimental launch systems, space research missions, small satellite launch concepts. The concept of a single stage rocket is important in aerospace engineering because it helps students to understand the fundamental principles of propulsion, aerodynamics, stability, structural design, flight mechanics, as well as the empathy based introduction to rocket systems here to explain. Understanding the rocket systems through human experience. Before studying the rocket systems technically, it is useful to understand them through an empathy based approach. Imagine a person trying to climb a mountain while carrying a heavy backpack. At the beginning, the movement is slow because of the heavy load. As food and supplies are consumed, the bag becomes lighter. The person moves faster with a reduced weight. A rocket behaves similarly. Initially, it carries a huge amount of propellant. As fuel burns, the mass decreases, acceleration increases gradually. In a single stage rocket, the rocket must carry fuel, engine, structure, payload throughout the entire mission without discarding any part. This creates engineering challenges: high structural weight, large fuel requirement, limited payload capacity, increased thermal stress. From an engineering empathy perspective, designers must balance performance and safety, minimize structural weight, improve fuel efficiency, ensure mission reliability, and reduce the operational complexity. Then the similarities between single stage and multi stage rocket systems. Although single stage and multi stage rockets differ in configuration, they share several common aerospace principles. As similarity propulsion, both are use rocket engines to generate the thrust. Fuel usage, both consume propellant based on the Newton's third law. Both require navigation and control systems. As well as, let's go to the next slide for need for staging. Need for staging rocket system. In rocket propulsion, staging is essential. The essential design concept is used to improve the efficiency, performance, and payload carrying capability of launch vehicles. A rocket stage consists of its own engines, fuel tanks, accelerator tanks, structural components, and associated systems. During the flight, once the fuel of a stage is completely consumed, the third stage is separated from the vehicle, allowing the remaining stages to continue the mission with reduced mass. The need for staging arises mainly because rockets must overcome Earth's gravitational pull and atmospheric resistance while carrying a large quantity of propellant. If a single stage rocket carries all the empty fuel tanks and structural weight throughout the mission, a significant amount of energy is wasted in accelerating useless mass. Staging solves this problem by discarding unnecessary weight during the flight, thereby increasing overall propulsion efficiency. The concept of staging is closely related to the rocket equation, which shows that the velocity achieved by a rocket depends on heavily on its mass ratio. A rocket with a lower structural mass after fuel burn can achieve higher velocity with the same amount of propellant. As each stage separates, the rocket becomes lighter, enabling the subsequent stages to accelerate more effectively. This is particularly important in space missions where extremely high velocities are required to place the satellites into orbit or to send spacecraft beyond Earth's atmosphere. Without staging, achieving the orbital velocity with the conventional chemical propulsion would be extremely difficult and economically impractical. Another important need for staging is the enhancement of payload capacity. Multi stage rockets can carry heavier satellites, scientific instruments, astronauts, and cargo into space compared to single stage systems. By dividing propulsion into multiple stages, engineers can optimize each stage for specific flight conditions. The lower stage is generally designed to produce very high thrust to lift through dense atmosphere and gravity, while the upper stages are optimized for operation in near vacuum conditions where efficiency becomes more important than the thrust. This specialization improves mission performance and reduces fuel wastage. Staging also helps in improving the mission flexibility and reliability. Different stages can be designed using different engine types, fuel combinations, and control systems suitable for various phases of flight. For example, boosters may use solid rocket motors for powerful initial liftoff, while upper stages may use liquid propulsion systems for precise orbital insertion. In advanced mission, additional stages are used for deep space transfers, lunar missions, and interplanetary exploration. Thus, staging allows engineers to tailor the rocket design according to the mission objectives. One of the major advantages of staging is the significant increase in rocket efficiency and achievable velocity. Since the empty tanks and engines are discarded after use, the remaining rocket mass decreases continuously, resulting in better acceleration. Staging also enables large payload delivery, making modern communication satellites, navigation systems, weather monitoring, and human space flight possible. Another advantage is the optimization of engine performance because each stage can operate under the conditions for which it is specifically designed. Staging further improves the fuel economy, reduces structural loading on upper stages, and enhances overall mission success probability. Reusable staging technologies developed in modern launch systems also reduce launch costs, recovering and reusing certain stages. Despite these advantages, staging also has several disadvantages. The design and integration of multi-stage rockets are highly complex and require sophisticated engineering. Stage separation mechanisms must operate perfectly during the flight. Any failure in the separation can lead to complete mission loss. Additional stages increase manufacturing cost, maintenance requirements, and system complexity. The use of multiple engines in the stage structures and control systems also increases the chances of mechanical or electronic failure. Moreover, discarded stages contribute to space debris and environmental concerns if not properly managed. So that's all today for today's class. In this class, we have seen about what is a single stage rocket system and the staging as well as the need for staging. What are the advantages and the disadvantages in this class? Thank you all.